Yeah. Welcome everyone. Does the sound work? Or okay, perfect. So no, here this meeting. Okay. I agree. The recording. So welcome everyone. Yes, this hybrid lecture is about digital media and chemistry lessons. And I thought here we have different points we're gonna focus on. Here's the structure first of all. I think we should clarify why do we really need digital media in chemistry lessons. Then I wanted to have a look at the media itself. What is media? What is multimedia? And how does it rely on and how does it depend on representations and the chemical terminology? Then I wanted to have a look at the theoretical frameworks, a cognitive perspective on the TPACK model, on the multimedia theory of Mayer, cognitive load theory. And yeah, last but not least, I think maybe the most important part for you, I want to give you some guidelines, some tips. How can you implement digital media purposefully in their classroom? And yeah, for that, I have an example at the end. This is an AR learning environment, and I want to give you a short insight what I did in my PhD project, and yeah, maybe how you can implement innovative technologies very meaningfully in the classroom. So let's start with the first question. Why do we have to incorporate digital media into subject teaching, or especially here chemistry? I thought, okay, let's start with a quote as a short motivation. This is a quote from Hoover and Banieri. They said, digitalization is currently affecting us more than almost any other issue in the last decade. With the publication of Competences in the Digital World, the topic of digitalization has finally arrived in all school subjects. And as the quote highlights, digital competence has now fully entered all school subjects. I think this is a very important part. And this makes necessary for us as educators to integrate digital tools, not just only as add-ons, like, okay, let's make it a little bit digital. No, we have to integrate it as elements of learning environments, and we have to make sure that we really promote learning processes. So if we have a look at this quote, we see competences in the digital world. Maybe you already heard it. In Germany, we have digital competence expectations for pupils. And according to the KMK, students must develop 6 competence areas. So the first one is to search, process, and prepare information. What does this mean? Of course, you use a digital tool and you do some research with that. You get some information, you have texts, you have pictures, and you put out what you need for your learning process. The next second part is the pupils have to communicate and to cooperate with digital media. I think a very understandable or easy to a competence area easy to understand, because if you use a digital tool and you want to talk to anyone other over distance, yeah, this tool makes it easier, and you design new you design new materials by the help of the digital tools, and this is close to the next competence area, produce and present. So if you want to promote inquiry-based learning in the classroom, you use a digital tool, especially a tablet, an ebook. And what do? You want the pupils to have a self-regulated process and to take some pictures of the experiment, to write down some notes and do everything by themselves, and to collect the information they have regarding the experiment, put it together in a digital version. What ebook, eScript, for example. So the last areas we have is, of course, the pupils, they should be aware how to protect and to save the data they get. Then how to solve problems and take action. What does this mean? If the digital tool doesn't work, sometimes it happens, they have to find a solution by themselves how they can go on in their working process, their learning process. And last but not least, the last area is they always have to analyze and to reflect if the digital tool is really necessary, if it makes sense to use it in the learning process. I think in a time when, or currently, when we focus on artificial intelligence, this era is so much more important than I would ever imagine it would be. So if you think about the digital competencies for pupils, I think it makes sense that teachers also should have digital competencies. And this part of the slide shows the TPACK model, the Technological Pedagogical Content Knowledge by Mishra and Köhler. And it reminds us that teaching with digital media is only successful if you combine these three aspects: pedagogy, technology, and content knowledge. Let's have a look at this. Many chemistry concepts are very, very abstract, and they are not accessible for pupils. Maybe you know the Chomsky triangle. We have the macroscopic, we have the submicroscopic, and we have the representative level. What do? We can observe the real world, real chemical, scientific phenomena, and if we want to explain the macroscopic world, we have to use the submicroscopic world. And this is something which is not that easy for pupils. And what do we do in this case? Maybe we can use technology to demonstrate the submicroscopic processes and to make them more touchable or accessible for students. For example, simulations, animations of something. So the next part is the pedagogy. Let's focus on that. Technology must be tied to sound teaching strategies to truly support the learning, and they shouldn't be some kind of decoration or add-on, as I already said. They really had to be implemented purposefully. And last but not least, the TPACK model says we really have to focus on the learner's prior knowledge. Technology can just help students in their learning processes if we really understand where do they stand and what mental concepts do they have, what prior knowledge do they have. And so you see, there are a lot of different parts that you as prospective teachers have to know. And in this new era, the digital revolution, AI is also a new part, and AI is becoming more present in education. And Mishra also said, okay, let's extend the TPACK model into AI TPACK, because now we really have to critically reflect about the use of artificial intelligence in the classroom. There are also other people or other organizations who focus on AI and the expectations of prospective teachers. For example, I picked out the AI competency framework for students by the UNESCO. And they say that AI brings new opportunities, but also new demands. And educational institutions should redefine the teachers' roles in the classroom and strengthen professional development. So the teachers, yes, of course, can effectively, ethically, and in a pedagogically meaningful way use AI. Here's a short quote, which I've already said. So last but not least, regarding the expectations of prospective teachers, I thought it's worth to have a look at the DICCOMP-EDU framework. This framework provides a detailed description of digital competencies for educators, and it starts by the professional engagement. Here, this is the yellow and it's the orange area, and goes to the learner's competencies itself. What does this mean? We have different competencies, and you can assess yourself and figure out where do you stand currently by doing this questionnaire, because if you want to use digital media in the classroom, in the school, you have to start by thinking about how can I cooperate with my colleagues with digital media? How can I support the classroom management, organizational stuff? This is everything which is here written down. And on the other side, you have to really promote the digital competencies of the learners. This is normally not always something to do with the subject itself. It really means they have to be aware, for example, how to use ChatGPT and how critically think about ChatGPT. And in the middle, there are the educators' pedagogic competencies. How can you support the teaching? Can you create a digital learning environment by yourself? Is it very meaningfully if you implement it in the classroom? So this is the middle part. And all in all, it builds a big framework and big competency parts, which are very important for you as prospective teachers. Let's go on. My next question. What are digital media and how relevant are they in the classroom? Now we know we have to implement them, but I think we also should have a look at the media and the multimedia. What is it? And here I focus on the media. At first, media are tools for presenting and transmitting information. In the classroom, they mediate communication and support the learning processes. They should support the learning processes, of course, and they always must be didactically justified. So please be careful. Don't use the tool just to implement it. This is not the aim. We really want to have it has to make sense why we implement it. Media should improve the learning outcomes and not distract or overload the learners. Let's go further. Maybe you already have an idea. Now we know this is media, information transmitting tool. What is multimedia? Multimedia delivers information using several different types of media. So we combine them. And we can distinguish three aspects when we talk about multimedia. The first one is multimedia involves presenting information through different sign systems, forms of representation. This can be a text, this can be an image, this can be a symbol or a diagram, graph, whatever you want. The second part is the reception takes only place by using different sensory modalities. We can see information and we can hear information. Sometimes in chemistry we can also touch. But normally, if we talk about multimedia, we try to combine these different sensory modalities. And the next part is that these representations can be delivered via technical and non-technical systems. So it starts from Blackboard, textbook, and goes over to tablet or maybe AR, VR classes. Let's have a look at Weidenmann's grid for a more differentiated description of media offerings. What you see here is I'm gonna differ monomedia, multimedia here, and go on with coding the sensory modality. And in the end, I thought it makes sense to add the immersion experience too. And what I want you to show is just how can we differ between media and multimedia. A medium itself can be a book, a tablet, a laptop, a smartphone, just a single item, hardware. If you combine different kinds of media, I already said this is multimedia. Maybe it's a little bit old school, but a laptop with a CD-ROM, yes, this is multimedia. And this was the start of multimedia, or with MP3 or a video recorder. Now I think we are more innovative here, and we combine hardware and software, and this is also kind of multimedia, because if you have a tablet and you have an app instead, this is also a form of multimedia already. So if we are in a monomedia, in the monomedia area, we just talk about text, images, or symbols. And yes, in the multimedia part, we're gonna combine them. We talk about multiple external representations. This is also, or this is especially the fact when we combine text and images, and also with dynamic representations, because then we start to have videos or animations. I already said the sensory modality is very important, and here a monomodal system just focus on visual or auditory, and if you combine these with audiovisual systems, we talk about multimedia modal system. And yeah, I think the immersion part is it's not that easy to differ, but multimedia is definitely more high, or has a more higher immersion experience through this interactive learning environments than a monomedium, because normally if you read, this is not that immersive, but maybe it can also be. Let's have a look at the different types of media. We differ between personal medium and impersonal medium, and the teacher itself is a medium. And I think he's the most important medium we have, because he produces speech. He can also write down spontaneously something on the board, and he uses a lot of different representations, and he uses a lot of different mediums. So this makes him to one of the most important mediums we have in the classroom. He uses impersonal mediums, like a model. I already said, okay, we have the Johnson triangle, and we model every time when we want to make a chemical phenomena more accessible. So we have various types of models in the classroom. Modeling is the key process of scientific literacy, I think, and it's very adaptable for inquiry-based learning. So this is one medium. Another medium, which is still very present in the classroom, is the school book. This can be analog, this can be digital. And why do we love the textbook that much as educators? Because it is a medium which is developed on the basis of the curriculum. So we know, this is the content we have to teach during the school year. So easy for us. The content is already in there. So the next part is you can use the textbook in the classroom, and you can just let the learners do some self-study at home. Then what we also have, Blackboard, the smartboard, and yes, this one is also very important. I think it supports the structure of the lesson, and it is very flexible to use, spontaneous or planned. And what I also have as another impersonal medium, I thought the auditory medium is important. Yes, MP3s, very old school. Now we have streaming services. This can be analog or this can be digital mediums we're gonna use. And yeah, we need a playback device now. I think this is a smartphone or a tablet, and we also can combine it with visual representations like images, and then we just go a step further and talk about videos, animation simulations. So all in all, I think digital media allow multi-code, text, symbol, pictures, and multimodal presentation of content, multimodal, written or spoken. So what you have to know, and I don't want you to go out the store and think, oh my God, more representations are better. No, they aren't. More media or multimedia isn't always better. Just be aware. You have to pick out for the special learning process what you think, how can this medium, how can this representation foster the learning process, and consider multimedia design principles, focus on the cognitive load, and we're going to talk about this later. This is a little spoiler alert now. And then you just pick what you think is it makes sense for the classroom. We also have a lot of other special possibilities that go beyond audio-visual presentations. So I talked a lot about animation simulations. Of course, we have training programs already, which really makes sense to implement it in the classroom. Tutorial systems here, I really think about feedback systems, AI. It can be useful, and of course AR or VR learning environments. Maybe someone of you already had AR glasses or VR glasses on his head, and yeah, we're gonna have a look at this later. So what I don't want to miss in this talk is I talked about a lot about representations already and about the modalities. And I want to have a look into the technical terminology itself. What is this? And technical terminology is an agreement between scientists in the respective fields. So if you are in chemistry, makes sense. The chemistry scientists did this agreement. We want to concise the technical terminology by using technical terms. What is a technical term? Redox reaction, reduction, oxidation. This is something very, very special for the chemistry field. And this helps us for an objectification of the language, so that it's international, that it's situation unindependent. And we see now, if we talk about the technical terminology, it's the scientific language. We have different levels of language. If you compare it to the everyday language, it differs completely. And what you have to do in the classroom, you have to find a mutual transition and teach the teaching language. So reduce the scientific language, focus on the prior knowledge on the learners, but don't no problem. Don't hesitate to do too much technical to use too much technical terms, or don't be too much in the everyday language. You have to find this didactic reduction in a good way so that it is understandable for all the learners. And the problem is, of course, that is not so easy for teachers, and it's not that easy for pupils. And it really depends a lot with the levels of representation. This is the part why it gets so difficult and complex for us because sometimes we gotta mix it up. Therefore, have a look at the holistic definition of technical terminology. And technical terminology encompasses all forms of representations used to communicate scientific topics. In addition to verbal language, this also includes pictorial and symbolic representations of specialized content. I think this quote makes clear why it is so complicated, what I already said. It's the representations, how to combine them, how to use them, how to change them into a new representation. And this is the part when the representational competence comes into play, because pupils should have the skill to interpret, to construct, coordinate, and to translate representations. And they also have to have, they also should be aware of how to change the representations and how to switch them into another. Kozma and Russell, I think this is the Bible of representation forms in the didactic field. They said representational competence allows learners to reflect the use of a variety of representations, singly or together, to think about it, communicate, and act on chemical phenomena. So I think this is really the basis of chemical terminology, and then in the end, how to use digital media, multimedia in the classroom. And of course, yeah, I already said it's not that easy for pupils. Let's have a look at the chemical terminology. What do we want to achieve with this? Just to make it a little bit more accessible for you. We want to name substances, describe properties, and feel free to think about how would you say that in the chemistry classroom. German, it's easier. We want to name chemical reactions and reaction types. For example, this one can be on the submicroscopic level with symbols, or maybe if you write down the words of every special compound, it's another text, it's another representation form, it's a text. We want to characterize the processes, the chemical processes, and of course we also want to describe the chemical work processes and methods. Here's just a short overview to see that we have text, symbols, pictures. And if we have, for example, a standard text, this is a continuous text, like a description of an experimental setup. Symbols, of course, the combination of letters and numbers, especially when we talk about a reaction, or a reaction equation, we write it down. Images, we can take a picture of a real image of a real experimental setup on the macroscopic level, but we also can take a picture of a model, and the model is natrium chloride, and this is on the submicroscopic level, for example. There are different abstractions we have, because a text is also possible to add in a diagram, so this is more abstract. If we talk about constitutional formula or reactional mathematical equations, this is also more abstract. And even if we talk about a schematic drawing, this is also more abstract. We have different dimensions, of course, can be 2-dimensional, 3-dimensional. In the image part, there we can talk about valence line formula, structural formula. Then we can add different dynamics. This is also a case more in the image part, but I also think it's possible with stop motion, for example, to do it with some symbols. And it gets very interactively if you have the option to click on a text, get further to another information, and then we are in a hypertext and we have a parameter selection. And this makes the learning process more self-regulated. Also, if we use a simulation. And just because I've talked a lot about the representations and the representational competence, I want to focus, and this is the last slide with this whole technical terminology part, I want to focus on the changes in representation. You always have to be aware when you are in the classroom and you hand out the sheet, experimental setup is given in a text form and the pupils, they should write down the equation. They should they should draw the picture of the experimental setup. They translate one representation in another. And here, Steudel, they said, okay, in the chemistry or in the scientific field, it makes the most sense to translate a text in a text, or a text in a table, or a text in an image. And you see there are different many types how you can change representations from the given representation into the resulting representation. And if you think about that, you will see that a lot is going on in the head, in the mind, when the pupils are forced to do this representational change. And this leads me to the next question: what should teachers be aware of when using digital media? I talked about the mind. Yes, we came to the cognitive theory of multimedia learning. This is Mayer's theory, which is based on 3 assumptions. We have every individual has dual channels for audio and verbal and visual processing. We know the working memory has a limited capacity, so it's just possible to process 7 items at the same time. And meaningful learning occurs when learners actively integrate information. So these principles are very, very important, and let's have a look at the dual channel assumption itself. What we see is here, we have the information which is given, it's multimedia information, and Mayer focus on the ears and the eyes. He says it's better for learners to use both sensory modalities. And if we have these informations, we're gonna process them in the sensory model. We select different words, we select different images, and then we're gonna organize them in the working memory with the limited capacity. And here we build the pupils, or we also, every person who reads something or hears to something, we're gonna build our own mental models. The mental model, the verbal one for the sounds, and the pictorial one for the images. And we just combine it with our prior knowledge, which is in the long-term memory. So this is Mayer's thinking of how the cognitive processing of information is working. While Mayer focuses on how the verbal and visual information should be designed to reduce cognitive load, Schnotz goes a step further, and what Schnotz does, he explains how learners mentally construct coherent mental models. So what you see here, it's not the combination of auditive and visual information, it's the combination of 2 representations, which mean the same thing. Here we have, for example, the text ammonia, and we have the image of ammonia. And you're gonna start to see this multimedia representation. You're gonna select the special informations in the sensory register, both, and you're gonna create your prepositional representation or your mental model. How do you do that? By constructing the models or by doing a model inspection. And what is now happening, imagine if the pupil has, for example, a wrong prior knowledge, something wrong in his mind, he combines his prior knowledge with some new information, builds a new mental model, and maybe in the end, this electron pair is missing because when he writes it down in the end, yeah, he had another idea of this ammonium. So you see that the one thing is the combination of the two types, auditive or visual representations. And then it's also important to build up the same content by using different forms of representations. And all of this shows us, and Meyer shows us how multimedia should be designed. And here I come to the last part of the cognitive perspective. It's the cognitive load theory. And this theory explains us why the design matters by distinguish between three different cognitive loads. We start with the first one, it's the intrinsic load. And the intrinsic load stems from the material itself. It's the complexity of the content and the element interactivity. It cannot be changed, it cannot be redesigned by the teachers. This is the content. You can't change it. What you can change and what you really have to reduce is the extraneous load. This is the design of the learning material. So, yeah, we have to minimize the extraneous load. For imagine if you have a really complex content and then you use a lot of pictures and a lot of hypertexts, it gets too confusing and the design doesn't fit with the content and the learner is overloaded. So we have the intrinsic load and the extraneous load should be very reduced. The germane load is the mental effort devoted to building schemas, and it can be increased through productive cognitive engagement. So such as elaboration or interactive tasks. And all in all, we have these three different loads, intrinsic, extraneous, and germane load, sum up all together to the cognitive load. And our goal is to reduce the extraneous load and to manage the intrinsic load. This is also the part when we talk about didactic reduction, so that the learners have enough free capacity to engage meaningfully. And this leads me to the point of implications for design principles. And I always focus on these principles when I create my own learning environment. This one also based on design principles. The first important design principle is the multiple representation principle. It says that the combination of texts and pictures can help students, learners to learn in a better way. The next part is the contiguity principle. It says when giving a multimedia explanation, present corresponding words and pictures contiguously rather than separately. Makes sense? If you have a picture there and the explanation there, put it together. The modality principle says when giving a multimedia explanation, presents words as auditory narration rather than a visual on-screen text. So yeah, sometimes it's better to just hear it than to read it. And now you think maybe, I'm more the book type. I don't want to hear the podcast. I'm more the book type, for example. It depends on how is your prior knowledge, how secure are you with the topic. The next part is the coherence principle. When giving a multimedia explanation, use few rather than many extraneous words and pictures. Of course, just reduce it to the very simple. It's a little bit similar to the redundancy principle as we see. Then we have the split attention principle, and this one says support of a mental integration of text and image through the physical integration of the text. What does this concretely say? If you have a text here, if you have if you have an experimental setup here and you have the explanation here, what does happen? You have to switch your eyes the whole time between these two mediums, and this is getting very confused. So try to combine it and try to reduce split attention. And the redundancy principle says, if a single modality, self-explanatory and additional source of information is redundant. Yes, we focus on the important parts. And what we don't do is have this naive assumption. It's not always better to see and listen in the combination. It's not always better to do it by yourself in the end. It always depends on your prior knowledge. And this was the last design principle. I forgot, the individual differences principle. That says that all of the foregoing principles are more important for lower prior knowledge learners than for high knowledge learners, and for high spatial than low spatial learners. If you have a high prior knowledge, you don't have to put in a lot of different representations of media. If you have a lower knowledge learner, you're gonna do that. So, and what can we as competent teachers, how can we use digital media in a meaningful way? Here, I thought it makes sense to talk about the SAMR framework by Puente Dura. And what we're gonna do here is we differ between 4 steps, and we want to figure out when does it make sense to implement a digital tool in the classroom. If you use a digital tool just like an analog one, what would this be? Instead of the school book, I use a PDF document. You just substitute. The digital tool replaces the analog one. It makes no didactic, or it's not didactically justified why you use this digital tool. For me, it makes no sense. You can do this, but this is not why we should implement digital tools. If you use a digital tool that replaces an analog one and has additional functional features, then it makes sense. What is this? If you have a learner with a lower knowledge and he needs help because he is more the hearing type, and you're gonna add audio into your the audio function, just to the text shouldn't be just read, you also have the possibility to hear it. Then there is an additional function, and you augmented the analog one. And it makes sense. You improve the learning. You can also reconstruct, redesign the learning tasks, and then we talk about modification and redefinition. This is when we use a digital tool which enables tasks to be redesigned, like, oh my God, I can see the submacroscopic level and the macroscopic level. Think about that later when I show it to you. Then you're gonna modify new tasks. If we use digital tools which enables totally new learning environments, for example, when we had during COVID, there was no way to work together in the same space. What did we do? We used Microsoft Teams, Zoom, iServe, and we suddenly had the opportunity to work together, to see each other, to work simultaneously, cooperatively, and at the same time. This is redefinition because there was the digital media allowed us to build totally new learning environments, virtual classroom. I bring together the ICAP model and the SIMA framework to illustrate how different levels of cognitive engagement align with different types of technology integration. So what we're gonna have here is the SIMA framework, substitution, augmentation, modification, redefinition. And what we have here is the ICAP. So we talk about different learning activities and we combine them. And this is what I want you to do in the future when you think about, oh, should I really use this digital tool? Should I really use this simulation in the classroom? What learning activities do I promote? Do I promote them or aren't they really useful? The first question and the first learning activity is the passive one. This setting here, it's a very passive learning activity because you're just listening to me. I hope you are in an active mood, but I don't know because maybe you are just listening and don't thinking about anything I say. I think you are in the active learning activity because this one says, oh, I do some notes. I think what she says. I combine the words that she says. And this goes a step further. If you now start to think what is in my long-term memory, then you're gonna integrate all informations with the new informations. Maybe you think about the Johnson triangle and try to understand, how does it fit and how does it work together. Then you are in a constructive learning activity. And if you're gonna talk with your neighbor and share your informations in a peer group, then you are interactive. And here, it's not the other way around, but at the SIMA framework, I think redefinition isn't always better than augmentation. Can be, must be. ICAP, yes, here it is. The interactive learning normally is always better than a passive one. I don't want to say that passive isn't allowed because I think if you learn vocabulary, just baum, tree, you translate it into different languages. It totally makes sense to do the passive one. But normally when we want to learn scientific, when we want to focus on scientific literacy, go deeper into the chemistry learning, then we extend this. So let's come to the last point and maybe the most accessible for you, because we're gonna talk at the end about augmented reality and innovative technology, and I want to tell you what were my thoughts when I created this app, because there's a lot in it about the design principles and the cognitive perspective. But first of all, what is augmented reality? We have two poles. We have the real environment on the one side, and we have the virtual environment on the other side. Here, this classroom where we are currently in it, this is a real environment. I can see, I can touch, I can smell. This is real. A virtual environment is when you are totally in the virtual world. My first virtual experiments was when I was in Paris. I walked down the Champs-Élysées. It was a Samsung store, and it's a true story. And I think this was the part when I thought, oh my God, I want to do something with augmented reality. And then I went into the store. They gave me glasses. They said, okay, Melanie, just sit down there. Okay, and I did that. And then I sit on a chair, had this glasses on my head, and I was in an underwater world. And I was in a boat, and the whole boat was shaking, the chair was shaking, and I really feel to be part of this underwater world. And I was so afraid when a fish, a shark was swimming. Yeah, you were laughing. I really was afraid. So I thought, I'm in this underwater world. So the real world, Paris, Champs-Élysées, Samsung store, Nothing was visible for me, and it wasn't in my mind. I was totally in this immersive experience. This is virtual reality. If you combine these two words together, we are talking about augmented reality. Augmented reality is the moment when you are in a real environment, like we are here right now. But if you use a tablet or you use your glasses, you can see a virtual object. I think Pumuckl, if you know it, it was in the screen, but this was some kind of first AR experiments. When you are on Instagram and you do this filter function and and load up your post with, I don't know, dog ears. This is AR. And AR can also be used in the classroom, of course. Why? Because I think it can, for example, promote the understanding of a substance particle concept. And why can it do this? I think AR has different functions, like we could not just only use two-dimensional objects, we also can use three-dimensional objects. That means the virtual objects, which are really in the room right now, when you look through the tablet, you can see them from different perspectives. You can also interactively work with them. You can touch them, you can zoom them, you can make them smaller, you can just work with them together, and this supports your self-regulated learning. And maybe the most important part for me in my setting, as you will see soon, is there is the dynamic part. You can really combine it into real processes which are going on in the real world. So imagine if you have an experiment and you imagine in this YouTube, there is a zinc iodide solution in it. What happens after switching on the dB power source? What will happen? On the anode, you will see yellow iodine streaks. You will see on the anode that zinc dendrite is built, and this is just a macroscopic level, and it goes on in a long process. And what I now want is, or what I wanted during my PhD project, I wanted to combine the submicroscopic level and, of course, the submicroscopic level. These are the particle processes which are normally not visible for us. And I wanted them to combine it to the real world. So I used the dynamic function of AR to combine these two different worlds together. And I focused on the cognitive psychology perspective too, because I thought it totally makes sense to put the submicroscopic and macroscopic level together. No, I don't want to mix them up because I don't want to create wrong concepts, misconcepts, but by saying the submicroscopic level is always virtual and the macroscopic level is always the real world, I can differ between the two words, but I also can combine it, and I can make sure that there is the contiguity principle and there is the coherence principle, which are really working. Spoiler alert, I thought I can reduce split attention, and the split attention effect will be so big I could measure it. Split attention was no effect, but augmented reality was really good, not worse than a simulation. And this also it was a good result for me because it showed me you can really use augmented reality to promote the substance particle concept understanding of learners. And now we're going to have a short look into my learning environment. So Yeah, as I already said, normally there would be the power source, maybe normally there would be a solution in it, but I think just for the understanding how I combined the digital, the submicroscopic processes into the real world, I think you will understand this. Oh, I'm gonna assume. Sorry. No. So, as you also can see here, I compared augmented reality with a simulation just to figure out if AR is really better or worse than other not that innovative technologies. Now we're going to have a look at AR. So this is just for me. You always detect the learning environment to make sure that we really can see what we want to see. And I hope it will work. So I had an app with 4 learning paths. We have before switching on the power source, after switching on the power source, and before we're gonna switch it on, we have just the experimental setup informations like, okay, what chemicals do we have? What is the equipment? Of course, here are the electrodes, it's the YouTube. We also have some more informations, everything you know when you do an experiment, of course. And you always have small tasks just to make sure that the learner is in the learning environment, like here, just to describe the real experiment on the macroscopic level in this case. For me, it was important to have a look at the submicroscopic level. And what you see here is I always differed between the types of representation: text, symbol, picture. And when the power source is off, we just see, okay, we have our zinc cations and our iodide anions, and they are just moving around in the sense of Brownian motion. So this is the text. What do you think? Is it abstract? Maybe. No? Okay. For pupils, I think it could be abstract. This was the reason why I implemented this one. Here, the Superloop is coming, and we're gonna see, okay, anions, cations, cations are moving around. We can have a look from different perspectives. And of course, I also did here the job of didactic reduction because I thought, is it necessary to add the water molecules? I thought, no, hydration is another chemical concept, makes no sense to talk about that right now. And after switching on the power source, what would you see? I've already said it. On the macroscopic level, you would see that on the anode side, there are yellow iodine streaks which are forming, and we would see that on the cathode, there is a zinc dendrite growing, and on the submicroscopic level, we would see that here is the reduction oxidation, the redox reaction. And of course, if we want to see the symbols, we would here have a deeper look and could recognize the 2 anions are giving, each other is giving away 1 electron. The electron is moving. And of course, normally there would be some cables, of course, connected to the power source. Just add it in your fantasy, and we see, aha, here is an iodine molecule built, and here we can increase or decrease the voltage, and we also can see it on the picture level, and it's the same part. And just a short look at this one. We also can combine it with the reactions itself, and we would see, okay, here's a zinc atom, and here are two molecules are already built. And yes, what I wanted to do, or what I did, is I combined with regarding the contiguity principle, the coherence principle, submicroscopic and the macroscopic level. And I thought it would be better if you combine it here instead of having the tablet here, the simulation, the setup here, and you are forced to switch between these two mediums. But as I already said, that was no effect. So, yeah, with this short example, I hope, you want to try your own learning environments. I think this one, it was very complicated to program it, and it took a lot of time, but with small ebooks, with nice videos, I think we have so much opportunities to create innovative, meaningfully, didactically justified learning environments. And yeah, I hope you had fun and you try it out. If you have any questions or anything which lies on your heart and you want to share with me, please feel free to ask me.
I would definitely say thank you, and also remind the community online that you can ask questions. I think Janus would read them out if there are any. Really, thank you very much for your talk and the presentation of your nice tool that you created.
Thank you.
Are there any questions here in the room? I can also translate them if you don't feel comfortable in English.
I just have a question about the app. Is it possible to like take a screenshot or to pause while looking at it? Because I felt like, especially if you hold the tablet, for example, if you can't put it somewhere stable, that you get a little bit of motion sickness trying to read the text, because it's moving around, and it would be maybe, I mean, if it's not possible yet, do you think it would be possible to do like a little pause button or something to actually have the text still on the screen?
Chiara, thank you for this question. It's a very good question, and I have thought about that a lot. So first of all, I had a stand.
Okay.
So maybe
yeah, that would be
okay.
Yeah.
But a stop button didn't make sense for me, because what happens in the real world? It goes on. So if I stop the submicroscopic, the processes of the particles, I can't stop. Okay, maybe I can stop if I switch off the power source, but this is maybe it would be an option, but I wanted the learners just do this experiment, how you do it, and it will go on. And if there are more streaks built, it's more yellow. So for me, the stop button didn't make sense, but I understand what you mean. And if you do that, you really have to make sure that both levels have the same option.
Yeah.
Yeah. And I think it's also different. I also had the head-mounted display technique. This is the technical term for AR glasses, and there you have a total out of this feeling differs completely, because here you have the frame of the tablet, of the screen, and if you have the AR glasses, yeah, it's more immersive.
Thank you.
Okay. Are there any questions online? And then if there are no questions in the room anymore, I say thank you very much for coming and for joining online. Thank you very much for your talk, Ellie. And
thank you.
I wish everyone a nice day online, and for the class here, we go on.